The universe seems to be perfect, at least from what we can see in our equations describing the universe. Ever since it started in the Big Bang 13.8 billion years ago, everything seems to be working out with perfect precision. Galaxies were formed, planets came together making up solar systems, and life itself had took place on planet Earth. But why is all of this happening? What's truly guiding this process of precision? It all comes down to this one equation in physics that I believe, at least in my opinion, governs every little equation we have describing reality. It is the basis of everything we've ever known, and it seems to be controlling everything we have written down as a mathematical description of every motion in the universe. I will show you on the blackboard behind me how nature tends to be working out these calculations, which all comes down to this one principle that is called the principle of least action. This principle started off as a philosophical question rather than pure science, and it was posed by the scientist Pierre-Louis Maupertuis, in which he argued that nature seems to be working out in an efficient and economical way. He tied this notion to the existence of God, as every scientist done in the past, where he thought that the way that nature is working out in this regard seems to be tied to an intelligent creator, as only an intelligent creator is capable of designing a universe where every motion in it is economical and efficient, where it gets to the point rather than taking random paths and wasting energy. Of course, this claim was faced with mockery and humiliation, as a lot of people didn't agree with this scientist that it should be tied to a god. A lot of people did not like him tying science and religion together and attributing these physical laws to a creator. One of these people was Voltaire, who mocked this scientist in public and called him a crazy man for saying these things, and he said that you should separate science and religion and keep philosophy away from theology, and Voltaire did not like theologians, of course. So this principle started out as philosophy and then it became mathematics, which is crazy because a lot of people say that science and philosophy are very distinct, but they're actually very, very close to each other. Philosophy gave rise to science. Science was philosophy, and then over time science took a different course than philosophy, and philosophy became an art rather than pure science, but actually it has way more radical ideas that could help science advance way more than mathematics, at least in my opinion. Now, just to get things started, the principle of least action, which governs all of our equations, it's in every equation, especially in Newtonian mechanics, particle physics, Maxwell's equations, relativity. So the most basic principle of this equation is nature is efficient somehow. Nobody knows why. But just to start things off, so what this means is that nature chooses the path for which action is stationary. And the equation of the principle of least action, which was later formulated by Euler himself, which kind of, I feel like Euler is the guy that took the Pierre-Louis' idea from philosophy to actual mathematics, which is crazy to me. Like, you can actually see that step of changing from philosophy to physics. And this equation is given as S equals the integral from t1 to t2 of L dt. Now L here is the Lagrangian. The Lagrangian has all the information about the energy of a certain system. So this is the action here. So what this principle states, that in any system in nature, this has to be balanced out. It has to be stationary. But what does this mean? Why does it have to be stationary? What this means is that this L is described as L equals T minus V. T is the kinetic energy and V is the potential energy. As we know in every system, like for example, if you throw a ball in the air and this ball comes down, it takes a path, and that path itself is described by this equation. And this eraser, for example, or the ball in what I just said, when it goes up to the air and it comes down, there is these two energies that are playing out. There is the kinetic energy, which is me throwing the ball, and then the potential energy, which is when the ball reaches the highest point, which have a potential energy that brings it down. So what this principle says, the reason why this ball takes this specific path out of infinitely many possible paths is so the kinetic energy and the potential energy are somehow balanced out together, so there is no loss, no escape of this energy. So basically, if you want to graph this path of this ball, it would look like this. It goes up and then it comes down. And this is the scenario for everything that you ever throw in this universe. This is how it works. Planets, galaxies, stars, this is how they orbit. It's all governed by this little equation. It's so small. So you might question, why is it specifically this path? Why not, like, why doesn't the ball go like this? Or go like this? Or like this? It's because of this equation. Because this path has this perfectly tuned. It's as if the universe is going through this path, seeing this path if it's truly good for itself, if this path is working out. And then it comes down to this path and it's like, this is the perfect path for everything to work out and to become efficient, to work out perfectly and balanced out, mathematically consistent. So just to take things forward, I will derive for you the equation that describes the motion of the ball being thrown in the air and coming down, and you will see how beautiful it actually is. So for a ball being thrown in the air through an upward uniform gravitational pull, which is where we live on Earth, the principle of least action gives you the actual trajectory. So you're starting from the equations and then you are reaching to this path here. You don't know how the ball is going to work out. This equation will give you how the ball will look like, how its trajectory is going to look like. So as we said before, the Lagrangian is t minus v. Now L, we need to write down what T is and what V is. And we know that the kinetic energy is half m of the speed squared minus mgy, which is the potential energy. So this is potential and this is kinetic energy. So kinetic energy minus potential energy. So we know that we need to vary the path as the ball is changing in time, the position of the ball is changing in time. So y of t is varied by sigma of s equals 0. So the action, the variation of the action is 0. It's not changing. And this gives us the Euler-Lagrange equation. The Euler-Lagrange equations are the equations of motion that tells us everything we need to know about how the motion of a system would look like. So this is given as d over dt of the partial differential of L over the speed minus the partial differential of L over the position equals 0. So then we compute each term here and we put it back into the equation. So we know that the partial differential of L over speed is m over this. So when you find the partial differential of this, you get this. And then we need to find the derivative of this term again. So you multiply it with d over dt, because we need this part here. And this gives us the second derivative of the speed, which is acceleration. So this is the term that we have for this. Now we find this part. So the partial differential of y is minus mg. So we have these two now, and these are important for our analysis. So now you bring all of these together into this equation and see what happens. So this we have as m of dot dot y dot dot minus mg minus with minus is plus equals 0. So this is the equation here, and then what you do is you remove the m's, they cancel out as if you take this out, and you get this term. The acceleration equals to g. Acceleration equals to g. We know this from before. If we take in high school physics, we know that the acceleration of the Earth is g. Now you integrate over these equations. And when you integrate, what do you think you will get? Try to think about it. It's a trajectory. As we know, it should look like this. So let's see what we will actually get. So the integral of acceleration equals the integral of g, and what this gives us is s equals the integral of minus g over dt. As we know from, this is the action, this is minus g here. And if we integrate this over time, we would get v naught of t minus half of gt squared plus y naught. And this is the equation that governs the motion of the ball being thrown in the air. And from this, we conclude that this is actually the path, when we graph it, of a ball traveling in air going to the ground. From this equation, like we know that nature is telling us that, oh, this is the components of every symbol here coming together gives you the most efficient economical cost for a certain path taking place in nature. So if you want to think of this principle in a different way, you can think of it as the kinetic energy being played out here wants the path to be smooth as possible, while the potential energy wants to grab it to the ground because of the gravitational pull. So this action is the perfect compromise between these two forces acting on the ball, on the system. And this equation itself can be reformed again and again to play out in quantum field theory. It can play out in the cosmology equations, and it all comes down to this little equation, the principle of least action, to tell us everything we need to know about this universe with perfect precision and an economical efficiency. It's actually crazy now that I'm thinking about it, that everything we've ever known in physics, it all comes down to this one equation. So my advice to you, if you want to be a pro in theoretical physics, master this principle. It should be nature to you that when you see something going on, you can immediately think, how can I make it economically efficient and mathematically with less costs?